it'll cool a little too rapidly, right? And so what you'll do is you'll just pop open the lid, dump in the cold water, close the lid. Okay, don't leave it sitting open for a long time, otherwise you're changing the characteristics of the container, the calorimeter, and that's going to change the cooling trend here. And so at minute 6 we mix it, but the problem is it takes time to mix, doesn't it? And so at minute 6, you know, this thermocouple is now sitting in air. And so this reading here is not the reading of the water, but the reading of the air temperature. And so this reading is invalid. And so we discard this, right, point here. Instead, what we do is we extrapolate the temperature. And so if this trend continued, what would the temperature be right at the instant of mixing? And this temperature here, we're only going to get from the graph by extrapolating it out to 6 minutes. This is what we call T cold. This is the temperature of the cold water right when we mix it. What is the temperature of the hot water right when we mix it? Well, when we mix it, we pop off the lid, the thermocouple is probably in air at that time, and the temperature is going to drop down. And so this point here is not valid because the thermocouple is not measuring the hot water. In fact, we're in the process of mixing the hot water with the cold water. And so what we're going to do is we're going to extrapolate this cooling curve out. So we just try to draw a smooth curve. And this temperature here, which we don't have a data point for, is going to be T hot. So that's our hot water. And so this would be the temperature of the hot water right at 6 minutes, right at the time of mixing, assuming that it has this nice cooling curve. But you know, it takes time for the hot water and the cold water to completely mix, so it's homogeneous as far as the temperature goes. There are no, temperature gradients. And so we're going to have 100 milliliters of tea mix. And so we dump this water in here, and then what we want to do is to speed up the mixing process. We want to cap it and then swirl it or stir it with the thermocouple. Thermocouple is a stainless steel housed probe. But due to incomplete mixing, due to temperature gradients, what we might see here as we mix it, at minute 7, we might have a hot spot, we might have a cold spot, we might have a warm spot. And so would you expect it after mixing to cool down and then warm up? Does that make any sense? No, that's impossible. And so what we do is we ignore the initial points right after mixing and then wait for a steady cooling trend to be observed. In order to see the steady cooling trend, what I want you to do is the second deviation from the procedure. What we're going to do is we're going to collect 15 minutes worth of data. The procedure says to collect, I think, 12 minutes worth of data. But 12 minutes might not be enough. And so we collect about 15 minutes so that, all of this incomplete mixing, we can get past that. And so if you see points like this, this, we ignore those. And what we wait for is this nice steady cooling curve, and then we're going to back extrapolate this. Assuming it cooled steady, we're going to back extrapolate this and say if we could have mixed this in one instant of time, this would be the temperature of the mixture. And then it just cooled down normally from there. So we're collecting a lot of data here. Okay, why do we need that? Well, we need that to see what happens, because what's going to happen to the cold water? Well, the cold water is going to warm up, the hot water is going to cool down. And so what should we call our system? What should we call our surroundings? here? Well, it doesn't really matter, but for us, we're going to call the system the cold water. And so our system is going to start off like this. We're going to have 50.0 milliliters of H2O liquid at T cold. And then our system is going to warm up here. So we'll end up with 50.0 milliliters of water at T mix. And so we went from T cold to T mix. And so some amount of heat was added to the system. Okay, how much heat was input into the system? Well, that depends. Is our system an object or is our system a reaction or process? Our system's an object. And so if we have an object, the heat depends on the amount of object times C times delta T of that object. All right, the amount of objects is 50 milliliters. We know the density of water to 3 sig figs. What's the density of water? 1.00 grams per milliliter. And so we have 50.0 grams of water, and we know the specific heat of water, 4.18 joules per gram. We know what delta T is. Delta T is T final minus T initial. And so we could calculate the amount of heat that must have been input into our cold water to warm it up by this temperature. Where did that heat come from? If this is our system, where did the heat come from? This is our energy level diagram. The heat came from the surroundings. And so what are the surroundings in this case? Write that over here. The surroundings in this case are going to be this. It's going to be 50.0 milliliters of H2O liquid at T hot. And so as the cold water gets mixed in here, it's going to absorb heat from the hot water. But not only is it going to absorb heat from the hot water, the styrofoam cups are also hot. In other words, our calorimeter is hot as well. And so it'll absorb heat from the calorimeter. And so what we say is our surroundings will be 50.0 milliliters of H2O liquid at T hot plus the calorimeter. The calorimeter are the styrofoam cups in the rest of the universe. And then this is going to go down to 50.0 milliliters of H2O liquid. The calorimeter is also at T hot. So they'll go to 50.0 milliliters of H2O liquid at T mix, plus the calorimeter will be at T mix now. And so we're going here, we have two objects now, the water and the calorimeter. And so this will be Q of the surroundings. Well, what is Q of the surroundings? Well, we have two objects. Q of the surroundings is going to be equal to Q of the hot water plus Q of the calorimeter. Over here, I forgot to write it down, but this is Q of the cold water. H2O cold. Okay, taking advantage of the first law of thermodynamics, energy is neither created nor destroyed. The amount of heat the system absorbed is the amount of heat the surroundings lost. So we see that Q of the system is equal to minus Q of the surroundings. Q of the system is Q of the cold water. Q of the surroundings is Q of the hot water plus Q of the calorimeter. Q of an object is the amount times C times delta T for the cold, minus Q of the hot water equals minus the amount of hot water times C times delta T for the hot water, plus the calorimeter. Well, the amount of calorimeter is only 1 calorimeter, so this is going to be C times delta T. So we pretty much know what C is. C, most people have this memorized, 4.18 joules per gram degree C. Delta T for the cold is T final, which is T mix, minus T initial, which is T cold. Delta T for the hot here is going to be T final, which is T mix, minus T initial, which is T hot. Now both the calorimeter and the hot water are in thermal contact, so they both start off with initial hot temperature, the same initial hot temperature. This is the same as that. The amount we know, delta T we got, and so the only unknown is C. So we'll solve for C. And C is going to be the heat capacity of the calorimeter. The mass of what? No. We don't weigh the calorimeter, because the calorimeter is not just the styrofoam cups. The calorimeter are 2 styrofoam cups, 2 lids, thermocouple, air, and the rest of the universe. And so how do you weigh the rest of the universe? The units don't work out. The units work out because the amount is going to be in grams, so the grams cancel. Delta T is going to be in degrees C, so degrees C cancels, and then we're left with joules. Inside the brackets, this term is in joules. C, when we solve for C, do you know what the C is? The units for C are? I don't know, did I talk about this? Heat capacity has 3 different common units. The units for C are going to be in joules per gram degrees C. That's called the specific heat. Joules per mole degrees C. That's a molar heat capacity. Or joules per object degrees C. Now the object could be bricks, so joule per brick per degree C. So if we have 10 bricks, then we know the heat capacity. But we're never going to have more than 1 calorimeter. And so if we only have 1 object always, then the object is 1, so the units are going to be in joules per degree C. And so the units here, when we solve for C, are going to be in joules per degree C, because there's only 1 calorimeter. We're never going to have multiple units of calorimeters. All right, so now we know, how much heat it takes, to raise the temperature of the styrofoam. The styrofoam cups are pretty good insulators, so it doesn't take much heat. They get in thermal equilibrium. It's the inside surface. All right, the next thing is, once we have that done, we're going to run some other experiments. And so the next experiment is going to be quite a bit different. In this experiment, we're going to put 50.0 milliliters of sodium hydroxide, AQ, plus 50.0 milliliters of HCl-AQ. And it turns out the molarity of the HCl is greater than the molarity of sodium hydroxide. And since the HCl is a little more concentrated, then this is the reaction we're doing. It's going to be sodium hydroxide plus HCl, and it's going to be excess HCl. Is going to yield sodium chloride plus H2O liquid. And so we're going to mix these two solutions together, and we're going to have this acid-base reaction occur, metathesis reaction occur. So what do we want to define as our system here? Well, what's going to happen is, what should we do? Should we pour the acid into the base, or the base into the acid? You know, normally when you do titration, you add the base to the acid, right? And if the concentrations aren't that concentrated, that's fine. But the rule is you pour the acid. You always add acid. And so what we're going to do is we're going to add the acid to this cup here. And so if we add the acid to this cup will be our calorimeter cup. We're only going to measure the T capacity of one of these. You'll have two of them. And they won't be exactly the same, so we've got to keep track of which cup we use. Okay, so this is our calorimeter here. And then how many milliliters of solution should we end up with, roughly? We're going to end up with 100.0 milliliters of NaCl AQ, right? Sodium chloride AQ from this acid base. But there's going to be a little bit of HCl, so we'll just say HCl and NaClAQ. Some acid won't react. And so when we do this, this turns out to be a exothermic reaction, that is, energy is released. So we're going from less stable to more stable products. All right, so this is going to be our system here. And the energy that's going to be released is going to be released as heat, which will go into the surroundings. And so when we look at our system is going to look a little different. We do the energy level diagram for a system. We're going to have sodium hydroxide plus HCl up here. At what temperature does this start off at? T cold, room temperature. And then it's going to end up as, you know, there's some excess HCl that's unreacted. Not much, a little bit of HCl plus sodium chloride. That's it. So some energy is released as heat. Okay. All right, what is the temperature of the products here? And so here's my sodium hydroxide HCl at T cold. Here's my HCl and sodium chloride at what temperature? T mix. This is going to be a T mix. Now, in the previous example, when we look at the energy change here, you know, U initial, U final. You look at this, and delta U, right? Delta U is a change in kinetic energy plus a change in potential energy. Is our system an object or our system a reaction? Our system's a reaction. When we do a reaction, we want to keep the change strictly in terms of potential energy. And so it's not a T mix, it's actually a T cold. And so we go from sodium hydroxide and HCl to sodium chloride and water. We've got the water, H2O liquid, and some unreacted HCl. But the initial temperature and the final temperature are the same because this is a reaction versus an object. An object, we don't want any change in potential energy, you know? And so H2O liquid is just as stable as H2O liquid. There's no change in potential energy. The change comes entirely in the form of kinetic energy or temperature. And so the Q for this is different because the Q, this is Q of our system, which is Q of a reaction. When we're dealing with a reaction or process, then it's not equal to the amount times C times delta T because there's no delta T, right? What is it equal to? Well, whenever we're dealing with a reaction, then we haven't really talked about this yet because we haven't gotten to delta H. But Q of the reaction is equal to the amount times delta H or the amount times delta U, depending on the conditions, depending on our system. And so we use amount times delta H under what conditions? Constant pressure. And so if it's constant pressure, it's delta H. If it's constant volume, it's delta U. Well, that depends. Are we doing this in a bomb or are we doing this in a coffee? We're doing this in a coffee cup. Coffee cup is constant pressure. You know, I don't think the coffee cups can withstand much pressure buildup, right? Any gas that's formed will leak out. And so in this case, we're doing it under constant pressure conditions. Q of the reaction is equal to the amount times delta H. But if you think about this, we're taking 50 milliliters of sodium hydroxide, 50 milliliters of HCl, and when you mix them together, we should end up with 100 milliliters of product solution. And so we started off with 50 plus 50, which is 100, and we end up with 100. And so, was there any change in the volume? And so one way of thinking about this is, if we did this in a bomb, would things be different? And so if we did this in a bomb, and I had some way to put my hands in the bomb and mix these two solutions together, would I build up a lot of pressure inside the bomb? Or would I build up a vacuum? In other words, you know, is there potential for an explosion in the bomb, or is there potential for an implosion in the bomb? You know, if it's not strong enough. And the answer to that is, it doesn't matter. You know, it doesn't matter if you do this in a bomb or if you do this out in the open. You know, because what we see is there was no change in volume either way. And so what that means is, under constant pressure, the volume was constant. That is 100 milliliters total before, 100 milliliters total after. And so under constant pressure conditions, if volume doesn't change, we call volume constant. And so in this case, it's both constant pressure and constant volume, which means that delta U and delta H are the same thing. The same number. That's different than KClO3. You know, yesterday you did KClO3, and as the O2 was being produced, what happened? As the O2 was being produced, it forced the water out of the Florence flask into the beaker. Right? And so the pressures could be equalized. But if you did that in a bomb, let's say what you did was you did that and you wrapped tape around a stopper. You know, so you just stoppered the test tube and then taped it up So any O2 that's generated would just be trapped in the test tube. So there was no outlet here. And so you just completely block it off. What's going to happen there? Well, as you generate the O2, the pressure is going to skyrocket, and hopefully it doesn't explode, right? By a pressure explosion. And so that's a big difference there, because, you know, there's a big difference in how the reaction proceeds under constant volume versus under constant pressure conditions. And in that case, we know that delta U and delta H are not the same. But if there's no difference, you know, in how this reaction proceeds, whether we do it in a bomb, i.e. a fixed volume container, or out in the open, then if there's no difference, then delta U and delta H are the same. We're going to talk about delta U and delta H much more later, but I just want to introduce it now because I'm using it here. Okay, where does all this heat go from the reaction? Well, the heat's going to go into the surroundings. And so how do we define what the surroundings are? So let's take a look at the surroundings here. Well, the surroundings are going to consist of the coffee cup calorimeter, but something else. And that something else is what happens to the system. You know, once this reaction stops, you know, once we've consumed all the limiting reagent, does the system still exist? And the answer is no, the system does not exist anymore, because the system has a finite lifetime. The system's a reaction, and once the reaction is done and completed, the system is no longer there. But you'd say, well, how can the system no longer be there? Because matter can neither be created nor destroyed. The way it's there is now what we do is we take the product solution, HCl, sodium chloride, the water that was generated, and so we call this the product solution. The product solution is part of the surroundings now. And so once the reaction is done, it dumps heat into everything else. Well, what's everything else? Everything else is the product solution plus the calorimeter. And so as that heat or the energy is dumped into the product solution into the calorimeter, then these two objects are going to warm up. And so the heat is going to come in here. And so the product solution warms up. So we start off at T cold, but the solution is going to warm up here. And the calorimeter is going to warm up to T mix. So what do we have? We have 100.0 milliliters of product solution. Right. And we're going to take this as one mixture here, and that is Q of the surroundings is going to equal Q of the product solution plus Q of the calorimeter. Q of the product solution is going to equal the amount of product solution. Well, what's the amount of product solution? 100 milliliters, right? Times C of the product solution times delta T of the product solution. And so we're going to do the same deal with the graphs. You know, we're going to monitor the HCl and the NaOH temperature. Hopefully they're pretty much the same, but they might not be. And then at 6 minutes, we're going to mix it. But you know, the initial temperatures here are going to be off. We're going to wait until we see a nice cooling curve and back extrapolate. And so here's the mix, here's the cold. So we're going to do the same type of graphing here. And we might have some unreliable data points out here that we'll ignore. And so we can get our delta T here. The delta T would be T final, T mix minus T initial, T cold. Plus the calorimeter. How many calorimeters do we have? We only have one calorimeter. We always have just one calorimeter. And so we don't need to write the amount. In fact, let's get rid of the amount and just call it 1 times C times delta T. The calorimeter is in thermal contact with our product solution. In fact, our product solution is contained in the calorimeter, so they're both the same temperature. They have to be, so they're in contact with one another. And so we have to make some assumptions here. And one is, how many grams of product solution do I have? In order to figure out how many grams of product solution, I would need to know the density of the product solution, but I don't have the density. Do you know the density of an HCl sodium chloride solution? No. And so we're going to make an assumption. And so the assumptions that we're going to make, like this. The first assumption is we'll assume the density of the product solution. Well, if it's fairly dilute, then it should be close to water. So we'll just say the density of the product solution is about the same as the density of pure water. And these are pretty dilute. It's like 0.1 molar. It's not that concentrated. Do we know the specific heat of the product solution? We don't know the specific heat, but if it's dilute solutions are close to pure water, we're going to say that the specific heat of the product solution is close to the specific heat of pure water. And so if we make these two assumptions, which are reasonable because water is going to be the main heat sink, then we'll have this. Okay, so we'll use the first law of thermodynamics. You know, heat lost by the system is heat gained by the surroundings. And we'll put it together like this. Q of the system is equal to minus Q of the surroundings. Q of the system is the amount. Well, actually, let me just do a little more. Q of the system is Q of the reaction. Q of the reaction is the amount times delta H of the reaction. You guys remember delta H? The enthalpy? We'll talk about it more later. Which is equal to, well, the surroundings. So this is going to be negative. Well, the first surroundings will be the product solution. So the amount of product solution times C of the product solution times delta T. So this is Q of the product solution. Plus the calorimeter. We only have one calorimeter, so it's C of the calorimeter times delta T. This is C of the calorimeter, this is C of the product solution. Different thing. We know what the calorimeter heat capacity is from the previous experiment. We know what delta T is from the graph. We make the assumption for these, so we know all this. What we don't know is Q of the reaction. So in this, we're going to calculate Q of the reaction, and then we're going to calculate delta H of the reaction. Delta H of the reaction is just Q of the reaction over the amount. Now the amount of reaction is going to be dictated by how many moles of sodium hydroxide were reacted, because sodium hydroxide is a limiting reagent. And so what we'll end up with is like something like kilojoules per mole of sodium hydroxide reacted. Since HCl and sodium hydroxide react in a 1-to-1 mole ratio, we could just say kilojoules per mole of reaction. Okay. Whereas Q is just going to be joules, some number of joules. So we'll have to figure out how many moles of sodium hydroxide. Well, that's not hard because you'll be given the concentration in the volume. Okay, the next Uh-huh.
For delta H, what is it? Q surrounding?
No. Q of the reaction. And so basically it's this whole term here. Once you get a number for this, that's Q of the reaction. Q is an extensive property. Q depends on the amount. Delta H is a ratio. In the report, you have to calculate both. So you calculate Q first and then normalize it per mole of whatever reaction. Okay, with this one, let me talk about the next calorimetry experiment. So far there's two. Each calorimetry experiment takes about 15 minutes of data collection plus all the setup time. Okay, the next one is this. We're going to take solid sodium hydroxide rather than sodium hydroxide AQ plus HCl. Solid sodium hydroxide you got to watch out for because it's pure sodium hydroxide. It's not dilute stuff. And so you don't want to inhale. It's a solid. You don't want to inhale the dust from that because it's also known as lye or drain cleaner. I mean, you can buy it at the supermarket, but we're going to have it in powdered form. It's hard to weigh this stuff. Do you know why it's hard to weigh? It's hard to weigh because it's so hygroscopic. What does that mean? It's so hygroscopic, it deliquesces. It means it sucks water out from the air. And so the mass will just continually increase as you try to weigh it. So what you're going to do is you're going to bring a watch glass to the stockroom window, and she has some sodium hydroxide in the desiccator. She'll take it out of the desiccator and weigh out the sample for you quickly. And then you want to use it quickly because if you let it sit on your lab bench, it's going to pick up a lot of water. Eventually it will form a little pool of aqueous sodium hydroxide in your watch glass, which you don't want. And so we never use sodium hydroxide as a primary standard under ambient conditions. You know, what was a primary standard again? Primary or standardization. Well, we wouldn't use it. And so, anyway, we're going to weigh out some sodium hydroxide. It's not going to be a lot, just x.xx grams. So around 2 grams worth. But I'll tell you, she's not going to try to get it perfectly at 2 grams. It's too hard. It's close enough. But you got to get this mass. Oops, not with HCl. Sorry, we're not going to do it with HCl first. We're going to do it with H2O liquid. Yeah, I think that's right. With H2O liquid, and you know what this does? It forms sodium hydroxide AQ. Is that a reaction? No, that's a physical process. But it turns out this process also releases energy. It's exothermic. And this process is called dissolution, or dissolving. And so sometimes when you dissolve something, it gets cold. Sometimes when you dissolve something, it gets hot. Well, this is something you would dissolve and it gets hot, right? Because energy is released here. And so what is the system? Well, the system is going to be this. It's going to be sodium hydroxide, solid. And this is going to go to sodium hydroxide, AQ. So is the system an object or is the system a reaction or process? System an object or reaction or process? System, oh, so we have some maybe hot sodium hydroxide. We have some hot sodium hydroxide and it cools down, then it releases the energy to the surroundings. Yes? No, she's going to give you cold sodium hydroxide. She's going to give you room temperature sodium hydroxide. So is the room temperature sodium hydroxide going to cool down below room temperature and release the heat to the, no. And so the system is not an object. It's not a hot object cooling down. The system is actually a process, because if you look here, we're going from solid to aqueous. And going from solid to aqueous, heat is going to be released. It turns out that I guess aqueous sodium hydroxide is more stable than solid sodium hydroxide. And so this is Q of our system here. When we look at Q of our system, here, well, we have some water here. Water. Is this a constant pressure system or a constant volume system? This is a constant. Well, let's write out some more stuff here. This is going to be x.xx grams. This is going to be 50.0 milliliters. So we're going to just pour it into 50.0 milliliters. So 50.0 milliliters is going to be in a calorimeter like this. So we'll just monitor the temperature of the water. At 6 minutes, we'll dump in the sodium hydroxide quickly and then stir it up. And so what we have here is this. Is this a constant pressure or constant volume? Are we doing this in a bomb or in a coffee cup? Coffee cup, so it's constant pressure. Constant pressure. Could we also call it constant volume? Is it possible to be simultaneously constant pressure and constant volume? Yes, it is. It is because, look at, we start off with x.xx grams of this, 50.0 grams of this, and we're going to end up with 50x.xx grams of this mixture. And so essentially the volume state, there could be slight changes, but those changes in volume are going to be minimal. And so essentially the volume stayed the same. And so when you have a situation where we have both constant volume and constant pressure, then Q of the system is equal to the amount times delta H, which is equal to the amount times delta U. In other words, delta H and delta U are the same thing. Well, where does all this heat go? All the heat goes into the surroundings. So this is our system. What's our surroundings? What's our surroundings? The calorimeter? K is going to absorb the heat. Anything else? Well, the thermocouple is part of the calorimeter. Calorimeter is pretty much the whole rest of the universe. But, you know, the bulk of the heat is going to be absorbed by the calorimeter itself rather than the rest of the universe. So if we didn't have a calorimeter, then it could just go wherever it wants. Try to contain it. Anything else? The solution. Because once the system has stopped dissolving, is the system there anymore? No. And so once the dissolution is complete, then there's no more heat release. And so whatever is left over is now considered part of the surroundings. So we're going to have 50 well, anyway, we're going to have our product solution, which is sodium hydroxide, AQ, plus the calorimeter. And this is going to be at T cold. And that's going to warm up, to, this is an object, sodium hydroxide AQ, and the calorimeter is an object, and it's going to go up to T mix. Right? And so again, we're going to have to do the data collection to see how the temperature changes with time, and then do the extrapolations together. And so this is our surroundings, Q the surroundings. Now Q the surroundings is equal to Q of the sodium hydroxide aqueous plus Q of the calorimeter. Well, sodium hydroxide aqueous is an object. It's just this hot, the solution that starts off cold and gets hot. And so the change is entirely kinetic. If you look over here, is there any change in kinetic energy? No, the change is entirely potential. The potential energy of solid sodium hydroxide in liquid water is different than the potential energy or the energy of aqueous sodium hydroxide. Over here, the potential of sodium hydroxide aqueous is the same as the potential of sodium hydroxide aqueous. The potential of the calorimeter is the same as the potential. Nothing changed in potential energy. The change is strictly all kinetic energy. And so sodium hydroxide is an object. Objects are going to depend on the amount of object times C of the object times delta T of the object. Now the amount of object is easy because for this particular object we have 50x.xx grams of object. But the problem is we don't know what the specific heat of sodium hydroxide AQ is at this concentration. Do we have that? No. And so we have to make some kind of assumption here. What assumption are we going to make about the specific heat of sodium hydroxide aqueous? We're going to say it's going to be close to the specific heat of water. Plus the calorimeter. How many calorimeters do we have? We have only one calorimeter. And so it's going to be C of the calorimeter times delta T. Now the calorimeter and the product solution are in thermal contact, so the delta T's for both of these are going to be the same. Okay? The product solution is sitting in the calorimeter here. Okay, so again, we have to collect 15 minutes worth of temperatures in order to just get two of them. The two temperatures that we want at 6 minutes. And so what are we calculating? What are we solving for here? We're solving for Q of dissolution. And so Q of the system is equal to minus Q of the surrounding. Q of the system is equal to Q of sodium hydroxide dissolution, or dissolving. And that's going to equal, what is that equal to? The amount times delta H of dissolution. And this is going to equal the surroundings here. And the surroundings are going to equal the amount of product solution times C of the product solution times delta T of the product solution. Plus, plus C of the calorimeter times delta T of the calorimeter. And so in the calculations, you're going to calculate Q, and then you're going to calculate delta H of dissolution. Delta H of dissolution is just equal to Q of dissolution divided by the amount. The amount of sodium hydroxide, well, you're going to get 2 units for this. You're going to get it in kilojoules per gram of sodium hydroxide, and you're going to calculate in terms of kilojoules per mole of sodium hydroxide. To get kilojoules per gram, you just divide it by x.xx grams, Q. To get it in kilojoules per mole, you have to figure out, well, how many moles is x.xx grams of sodium hydroxide? You can get it kilojoules per mole. We're going to do one more reaction here, and the last one will be sodium hydroxide solid plus, is that right? HCl. Thank you. Sodium hydroxide solid plus HCl AQ is going to yield sodium chloride AQ plus H2O liquid. Okay, HCl is going to be in excess here. And so the amount of reaction is going to be dictated by how much sodium hydroxide we use. So in this case, we're going to monitor, we're going to use 50.0 mils of the HCl solution. So we're going to monitor the temperature of 50.0 mils of the HCl solution. Okay, at minute 6, we're going to pop the lid and then scrape in our sodium hydroxide and mix this up. Swirl it, mix it with the bar. Keep the lid on tight so you don't lose too much heat from this. Then we're going to get some temperatures again. The temperatures of the HCl should stay fairly stable at T cold, and then it heats up, and then there's going to be some random temperatures, and then it starts cooling down. So you back extrapolate this, and you get it at 6 minutes here, 6 minutes here. So this is T mix, this is T cold. 6 minutes. And so what is the system here? Is the system an object or hot object, cold object? When the system's an object, it's either hot or cold, and it's either going to cool down or warm up. Is the system an object in this case? No, the system is a reaction. So let's take a look. System is a reaction. We're starting off with sodium hydroxide solid plus HClAQ. And again, the stockroom is going to weigh out a sample. It's going to be x.xx grams. This. Sodium salts are all soluble, so there's no problem dissolving it, reacting with HCl. The products of this are going to be sodium chloride, AQ, plus some excess HCl, AQ, plus water, and heat or energy, Q. This isn't under constant pressure conditions, but did the volume change? No. And when I look at it before, and after, the volume is pretty much the same. So it's under both, constant pressure, constant volume. And so the Q of this is Q of reaction, acid-base reaction or metathesis reaction. Q of the reaction is equal to the amount times delta H. In this particular instance, delta H and delta U are the same. No difference. But in the lab, they want us to calculate delta H. They don't want us to calculate delta U. Sometimes they want you to calculate delta U. Because what's the difference between delta U and delta H? Well, delta U is the total energy change. So if delta U is the total energy change, then what is delta H? The partial energy change? Well, we'll look at that later. All right, so this is our system. The system's a reaction. And since it's a reaction, we start off at T cold. We're going to end up at T cold. So where does all this heat get dumped into? The heat gets dumped into the surroundings. And so what are the surroundings here? The surroundings will be the product solution. And so the product solution will warm up. And the calorimeter will warm up. And so we got two objects here, the product solution and the calorimeter. They're both going to absorb the heat from this reaction, and the temperature is going to warm up. So we'll end up with product solution, warm product solution. And warm calorimeter. And so this is going to be a T cold, this is going to be a T mix. Well, we can figure out what the Q of the surroundings are. The product solution is just going to be equal to the Q of the product solution plus Q of the calorimeter. Two objects. And so using the first law, Q of the system is equal to Q minus Q of the surroundings. We get this. Q of the system is equal to Q of the reaction. Q of the reaction is equal to the amount of reaction times delta H of the reaction. Okay, the surroundings. Well, the surroundings are going to be the product solution. So the product solution is an object. Objects depend on the amount times C times delta T. Do we know what C of the product solution is? No, we don't. So we got to make an assumption. What is the assumption we're going to make? We're going to say it's about equal to C of pure water. The calorimeter is an object, and it's going to get hot. So we have one calorimeter times the heat capacity of the calorimeter times delta T. The calorimeter. And so delta T is just T mix, or T final minus T initial, T cold. And so in this calculation, we're going to calculate Q of the reaction, and we're going to calculate delta H of the reaction. We're going to use delta H of the reaction probably in 1 or 2 units, in kilojoules per gram of sodium hydroxide or kilojoules per mole of sodium hydroxide. So these are the main calculations that we're going to do. Okay. Any questions on this? So I'll go through setting up the lab class system with you guys, but just be prepared to finish the lab tomorrow. Just the data collection. You don't have to finish the calculations tomorrow. So we spent a lot of time talking about heat. Let's talk about work now. You know, because the first law of thermodynamics says this, that the total energy change is going to be the heat exchange between the system and the surroundings and the work exchange between the system and the surroundings. When we look at the work, there are different kinds of work. You know, we could have electrical work. We could have mechanical work. You know, electrical work generating electricity, mechanical work like lifting a mast. We could have sound being generated. That's work. We can have light being generated, or we could have this. We could have the natural work of a chemical reaction occur. What is the natural? What am I talking about? Natural work of a chemical reaction. The natural work of a chemical reaction is you can't avoid it. So this is unavoidable under constant pressure conditions. Yesterday, you did a reaction under constant pressure conditions. You did the generating O2 gas under constant pressure conditions, right? Was any work done? Yes, work was done because, you know, the O2 gas that was being formed had to force the water out of the Florence flask into the beaker. Does that cost energy? It does cost energy. Could you have avoided it? You couldn't have avoided it. Well, actually, you could have avoided it. You know one way to avoid that? If I just use a solid stopper and then duct tape it. Just tape a stopper onto the test tube so that, you know, the O2 wouldn't have to force any water out, do any work, right? But this, if I did that, what's going to happen if I duct tape a stopper around? You know, the O2 is going to be formed inside here, and eventually it's going to explode by a pressure explosion, right? And so I guess I could avoid the work by doing it under constant volume conditions, and then I wouldn't have to be pushing water around or blowing this or blowing that or doing whatever, right? But we aren't doing it under constant volume conditions. We're doing it under constant pressure conditions. Now, could you have avoided doing the work? Could the system have avoided doing the work? No. And so this is what we call the natural work because it's unavoidable. You have to do it. Well, you know, if you have to do it, well, how much work do you have to do? Well, the natural work of a chemical reaction is called pressure volume work. And pressure volume work is just given by this. The work is equal to the P external times delta V. And so it depends on blowing up a balloon. You know, you blow up a balloon, it depends on what the external pressure is and how big the balloon you want to blow up is. And when we look at this, well, pressure is in atmospheres usually, delta V is in liters. And so this is very weird, atmospheres, liters, but it turns out atmospheres, liters is energy. And so let me just tell you how we can relate atmospheres, liters to joules. The way we can relate it to joules is by knowing R. If we know that we have 0.08206 liters times atmospheres per mole Kelvin, this is equal to 8.3145 joules per mole Kelvin. And you can see the relationship between liters, atmospheres, and joules. So what we do is we just take 8.3145 joules per mole Kelvin and divide that by 0.08206 liters times atmosphere per mole Kelvin. And we end up with this, 101.3 joules per liter atmosphere. And so what that says is if you want to blow up a 1 liter balloon with an external pressure of 1 atmosphere, it's going to cost you 100 joules of work. Okay. All right, so we're out of time, so I'll stop here.